Hi everybody. So in today's video, I'm going to be deriving the Cox-Ingersoll-Ross model, which is used to simulate interest rates, and I'm going to be converting it to its closed form solution. So let me go ahead in my LaTeX editor and type in begin matrix. So I'll first type in the Cox-Ingersoll-Ross model, so that's dr of t equals alpha of mu minus r of t, the current interest rate, times dt, delta time, plus sigma dwt. So this is the stochastic differential equation for this model, and the first thing I want to do is distribute the alpha and the dt to simplify it, because I want to get the r of t on this side, and I'm going to show you why in a minute. So let me go ahead and add a new line, and then I'm going to do drt equals alpha of mu dt minus alpha r of t dt plus sigma dwt. Okay, so now I'm going to carry this over to this side. So it's going to be dr of t plus alpha r of t dt equals alpha mu dt plus sigma dwt. Okay, so now what I want to do is I want to multiply both sides by e to the power of alpha time. And I'm going to show you guys why also, because it's going to be used in some of the calculus that I'm going to do. So this is going to be e to the power of alpha time dr of t plus e to the power of alpha time alpha r of t dt equals alpha mu e to the power of alpha t dt plus sigma e to the power of alpha t dwt. Okay, so now if we notice this portion of the formula, we could see that there's some sort of product rule, and I'm going to go ahead and actually prove that right now. So I'm going to do I'll start off with e to the power of alpha t r of t, and then this will, the derivative of this, let me just do okay, so we're going to do this derivative for t, so that's going to equal, with product rule, it's going to be u v prime plus vu prime. So u is EAT, alpha t, and r of t is v. So that's going to be e to the alpha t prime. I'll just do I. R of t plus e to the power of alpha t r of t I. Do not, I'm just doing this because there's like a little glitch in the LaTeX editor, but do not try doing this. So then the derivative of e to the alpha t with respect to time is just going to be let me just add this arrow here. So it's going to be e to the alpha time times alpha delta time or no, oh yeah, e to the alpha time and alpha delta time, and then we don't take the derivative of RT, so that's just going to be RT plus, now this is going to be e to the power of alpha time times drt. So if we look closely at this function, we have e to the power of alpha times drt as here, and we have e to the power of alpha times dt times r of t. So yeah, that's the product rule. So now I'm going to come over here and just simply do e. So it's going to be the d for derivative of e to the power of alpha time r of t, and this is going to equal this whole thing. So let me just copy this. Okay, so now we can perform the integrals. So let me go ahead and make this bigger. Okay, so make it a bit smaller. Yeah, so we can see this. So the first integral that I'm going to do is the integral of 0 to t of d e to the power of alpha t r of t. So since it's in its differential form here, it's just going to equal e to the power of alpha t r of t. And this is going to be 0 to the power of t. So then I will do e to the power of alpha t r of t minus e to the power of alpha 0 r of 0. So we can see that this becomes e to the power of alpha t times r of t minus 0 times alpha is 0, e to the power of 0 is 1. So this is going to end up being just this equation, but just go ahead and copy this. But instead of the e, just get rid of the e alpha. Okay, so we have the first integral. So yeah, this is the first one, and r of 0, as we know, is the initial interest rate. So now I'm going to add a new line. So now I'm going to compute the integral of this. So that's going to be alpha mu integral of 0 to the power of t of e to the power of alpha t dt. So maybe I'm going to actually change this to s. Yeah, that's better. So then I'm going to perform a u substitution. So u is going to equal alpha s ds. Yeah, this should not be dt, this should be ds. And then it's going to be t fraction of 1 alpha oh wait, I forgot. I have to do du equals alpha ds. So then it's going to be t fraction of 1 alpha du equals ds. So now we could replace where it says ds here. So this is going to turn into a new integral, and it's going to be alpha mu integral 0 to time of e to the power of u, and then t fraction 1 alpha du. So now we can see these alphas will cancel out. So it's just going to be mu of integral 0 to t of e to the power of u du, which will then just be e to the power of alpha t minus e to the power of alpha 0, because I performed the u substitution. So this will end up being e to the power of alpha t minus, so 0 times alpha is 0, e to the power of 0 is 1, so there's going to be e to the alpha of t minus 1. Okay, so we derived the second integral. Now let's do the third one. So this is going to be, where is it? This one right here. So off the bat, we're going to do sigma integral of 0 to t e to the power of alpha s dwt. So this is actually not integratable. Like, I have to use numerical approximation, and once we get to the code, I'll show you how I'm going to do it. But I'm going to rewrite all of these back into the main equation. So that's going to be, I'll just call this dws. Okay, so now it's going to be e to the power of alpha t r of t minus r0 equals mu e to the power of alpha t minus 1 plus sigma. I'll just copy this integral over here. Okay, and then I'm going to rearrange the formula a little bit. Instead of doing r of 0 here, I'm going to add it back here. Okay, so we have this equation. Now, what I want to do is I want to get rid of e to the alpha time from this side and bring it over here. So the first thing I need to do is distribute this. So it's still going to be, this portion is going to remain the same, but it's going to be r of 0 plus mu e to the power of alpha time minus mu plus the sigma integral. Yeah. So now I'm going to divide everything by e to the r alpha t. So that's just going to be r of t equals r of 0 e to the power of negative alpha t, because I'm bringing it from this side to this side, so the exponent flips, goes negative. So then this is going to be plus. So notice we already have an e to the power of alpha t here, but if we put e to the power of negative alpha t, it's going to cancel out. So it's just going to be mu. But over here we have negative mu, so this is going to be negative mu e to the power of negative alpha t. And now for the last part, it's going to be sigma e to the power of negative alpha t, and then the integral 0 to t e to the power of alpha s dws. And now I could carry this over into here. So what I'm going to do is just copy this portion. Let me also add a break line. Okay, so this is where I'll simplify it. So it's going to be, you know what, no, scratch that. Let me just do it this way. Yeah, okay, so the first portion, I'm going to pull mu out of this, so this is going to be plus mu. So it's going to be 1 minus e to the power of negative alpha t plus sigma integral of 0 to t of e to the power of negative alpha of t minus s dws. Okay, so we have it. So this is the closed form of the Cox-Ingersoll-Ross model. We started off with this stochastic differential equation. We ended up here. So now I'm going to code this in a Jupyter Notebook. So let me, so I'm going to come here, copy this, and then I'm going to come to my Jupyter Notebook and hit escape, M for markdown, Let's put the closed form solution. Let me also make it large. Okay, so now let's code this shit. So this is going to be import numpy as np. Import pandas as pd. So now I'm going to do data frame equals pd.read csv. Let me make this a little bit bigger. Okay, yeah, that's good. So I'm going to load Treasury yield data, so that's going to be yields.csv, and then print df. Okay, good. So I got my data frame. Let me just delete this. So I wanna load 1 month Treasury. So x is gonna, I'll call this rates equals df 1 month dot values, and then I'm gonna print rates. Okay, good. So I need to divide this by 100.0. Actually, let me go ahead and print df.head. I want to see the dates in order. Okay, so yeah, this has to be reversed. So it's going to be -1. Okay, so yeah, they're reversed now. So let me just come over here. So now I need to define the parameters for like alpha and mu. Yeah, so this is going to be def params, and it's going to take no arguments because I have rates already up here. So it's going to be let's see. So I'll call this alpha equals 0, mu equals the mean of rates. But for alpha, this is going to be a little bit more tricky. It's going to be for I in range 1 to the length of rates. Oh, okay. Alpha plus equals, oh wait, I'll just call this top and bottom. I do need to pass, okay, yeah, I do need to pass some of the arguments, so this is going to be, here, let me just restart this. Def params, so it's going to take the argument of x, it's going to take the argument of time, n is going to equal x time n. Let me just start off with this. So top equals 0, bot equals 0, mu equals numpy dot mean x, and then it's going to be for I in range 1 to the length of x, it's going to be top plus equals x of I minus 1 minus mu times x of I minus mu, and then bot is going to be plus equals x of I minus mu squared, and then I'm going to come here and do alpha equals, so wait, let me come up here and first do dt. dt equals t divided by n. So then alpha is going to equal negative log of top divided by bottom divided by delta time, and I need R0, which is going to be x, the latest rate. So then I'm going to return R0 alpha and mu. Yeah, R0 alpha and mu. So now I need to come over here. Okay, so I called it. So this is going to, let me go ahead and print params of rates. The time, so okay, let me define my time function, time variable. So time, I'm going to forecast these for 30 days. So 30.0 divided by 365.0. N is just going to be equal to like 50. And then, yeah, because in the, yeah, I'm going to be using this n in the winder process. So then I will just do like print params of rates t and n. Okay, so I got my parameters. That's good. So I will actually call them as R0, alpha, and mu equals params of t, no, rates t and n. Okay, so now I come back here. I need to do the Simpsons method now to approximate this portion of the integral. So what I'm going to do is just come here so I don't have to keep scrolling up. I'm just going to do Command C. And then come over here, convert to Markdown, Command V. Oh, wait, let me make this large. Okay, so, yeah, overwrite that file. Okay, so def Simpsons, and it just takes the argument of x. So this, oh no, it's going to take alpha and the argument of t. Let me do pass. Let me just go ahead and generate okay, so I'll call this t equals numpy dot a range of 0 to t plus 1 divided by 365, 1 divided by 365, so print big T. Okay, so we have the times here for this integral. So in order to do this, I'll come here and I will first start off by declaring a variable called total equals 0, and then if I also have to pass n into this, so that's where the n comes from. So if n mod 2 is equal to 0, it'll just be n plus equals 1. And I should add that same constraint in here, so that way it always ensures it's an odd number. I'll do Command C, come up to here. Okay, so now this is simply just going to be for I in range n. It's going to be total plus equals, hold on, I need to declare a variable called C. So I'll do C equals 0. So then I'll do C equals 1 if I equals 0 or I equals n minus 1, else 2 if I mod 2 equals 0, else 4. And I'm going to print C. So I'm going to call Simpsons of alpha t and n. Okay, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Yep, I got it correct. So then this will just simply be okay, so I don't actually need this TA range one. It's better if I do it in here, so I'll do T. So I'll do T0, T1 equals 0, T, dt, we'll call it dtx equals T1 minus T0 divided by n minus 1. And then it'll just simply be sigma Oh, right. I forgot. I need to also return VI. So VI is going to be the volatility of the rates. Okay. So, oh, right. Okay, so let me just go ahead and run this. Okay. So V, T, and N. This is going to be VI. Wait, this should also have mu in. No. We don't need mu in this one. We just need volatility. So this will be total plus equals um, C times e to the power of negative alpha times, so this is going to be T minus I times dtx. And then the Weiner process is going to be dwt equals numpy.random.rand_n for random normal, and it's going to take the argument of n as well. So this is going to be times dwt of I. So now I'm going to come over here. Wait. Okay, so I'm going to come over here and do total equals volatility V times dtx divided by 3.0, Simpson's method constant scalar, times total, and then I'm going to return total, and I'm going to call this C equals Simpsons, so print C. Okay, so we can see that it's a very small number. Let me add like maybe like 2 times this, just to get like bigger differences. Um, 10. Okay, I'm getting very small numbers with this, but okay, sigma dtx3. Maybe I should just do this. I should do lambda u. No. Okay, so I'm gonna have to import random, so this is gonna be random dot rand int negative 30 divided by 10, and then this is just gonna turn into a function. Oh, it's okay. You know what? Let's not spend too much time on it. It's giving us a random number, so now that I got that, let me get rid of that. So now we have approximated this integral. Um, yeah, negative alpha, everything checks out. So now I'm going to come back up here, and I'm going to get these integrals. So it's going to be, so r of t is going to be, I already have r of 0. So r of 0 times e to the power of negative alpha times time. Is that what it is up here? Yeah, r of 0 e to the power of negative alpha times time. And then it's going to be plus, do I have mu? Yeah, mu times 1 minus e to the power of negative alpha times time. Is that the same formula? Yeah, 1 minus e negative alpha. Okay. And there's going to be plus c. So I'm going to print simulated rate of return. and it's going to be R of t. 4.37. So let's print out R of 0. 4.284. Okay. Oh, okay. Maybe I should do this. Maybe I should now, let's see. So I'm going to come here, and I'm going to call this yields equals df dot values -1. And let me do yields. Okay. So I will erase this first part. So this will be 1, and then divided by 100. No, dot values actually. NumPy D array has no. Okay, I'll come here and just do this all as .toList. Okay, good. So now that I have that, okay, because I'm going to plot the yield curve, like the predicted values from the simulated rate of return. So I need to call params. So yeah, let me so I want to change it across maturities. So it's going to be, I guess the only difference would be like alpha. Okay, so step 1, I'll define these as steps. Step 1, divide up the yields. Step 2, compute the parameters for each yield. Step 3, compute the integral. Okay, so yeah, let me just do this. For R0 in yields, okay, this is going to be the same. Oh, no, I didn't mean to do that. Okay. So I'm still going to use the same tn, but I'm going to change this up a little bit, so it's going to be params. So this is going to be params. Oh, actually, yeah, shit. Okay. So this is what I'm going to do. I'm going to call this groups equals 1 month, 2 month, 3 month, 6 month, 1 year, 2 year, 3 year, 5 year, 7 year. Yeah, I'm just going to do these. So then it's going to be df2 equals df of groups. So let me go ahead and print df2. Okay, good. So this is all going to be divided by 100. So I'm just going to do dot values divided by 100. Okay, got my yields. So this is a NumPy array. So now I'm going to do M. I'll call this OP equals df2 dot shape. Let me go ahead and print O and P. 108 by 9, okay. So get rid of that. So then I will do for I in range P. So R of 0, so rates are going to equal df2 of I. And then now I could do the parameters, so it's going to be R0, alpha, mu, and VI. So R0, alpha, mu, and VI equals params of rates, time, and n. So let me go ahead and print some of these. So R0, alpha. Okay, good. So we've got everything there. Now the next step is to get the I'll call this vol equals Simpsons. So Simpsons takes alpha, alpha volatility, time, and n. And then I'm just going to do this. So R of t equals R of 0, and then I'm going to do sim equals empty list. So this is going to be sim dot append R of t. So I got alpha, t, and then I have to add the stochastic component, so that's going to be plus vol. So then so df2 and sim are my variables. So I'll do this. I'll hit enter. V is not defined. Oh, VI, yeah. Okay, so now I'm going to import matplotlib.pyplot as PLT. So fig equals plt.figure, ax equals fig.add subplot 111, and then it's going to be ax.plot groups by df2 color equals red, label equals historical, and then ax.plot groups sim color equals blue, label equals simulated. Run it. It is loading, loading, loading. What is this error? Oh, df shit. df2 -1. And here we have it. So red is the historical yield curve. Blue is the yield curve that computed by the closed form solution. So yeah, actually it's been quite some time. I didn't realize that the curve was like has a slight inversion like this, but it is what it is. So yeah, I think that about wraps up this video. So yeah, I thank you all for watching my video. I'm gonna keep coming out with more and more good quant content, so stay tuned and peace out.